Well, thank you very much, Jim, and thanks, Tomo. I hope you know what you've gotten me into in this. When I think nano, it's usually something about this big. So I brought some examples from the world of buildings and also brought some things from other activities. But rather than just talk about size, I would say that buildings are very coarse structures. And coarse, I mean in the sense that they're divided into layers and systems. And there are a few obstacles to thinking of buildings as being integrated, fine-scale structures like one would associate with a nano-architectonic system. And I'll run through three of those problems. The first is the fact that, and it's very interesting that the morning started this way, the problem of the two-dimensional drawing. It's, for me and for many architects, our biggest enemy is the fact that we're designing things in three-dimensional space, often algorithmically, which is not just defining geometry, but also data. And we have to push all that through a two-dimensional process so then someone else can translate that back into three dimensions to build the building. And it's a very odd state that architects are in right now. And this problem of the 2D, which here you see in a drawing of a primitive hut by Laugier, is that it breaks everything down into systems. So you have a primary structural system, you have a secondary structural system, you have a cladding system. All of those systems are independent and they need to be coordinated. So the way most architects coordinate all of those independent systems in two-dimensional drawings is through modularity. And modularity means usually in the Renaissance it was a proportional subdivision of systems. So you would break things down by thirds or fifths or sevenths. With modern construction, that modularity became purely dimensional. And that kind of an approach we're all familiar with. It yields not just a modular system of construction, but it mandates a separation of systems. And one of the things that I've been most interested in is collapsing building systems so that you can start to leverage the cladding of a building as structure of a building, as environmental modulation of a building, rather than dealing with each one of those things as a separate layer. Then finally, the third problem for architects with buildings is just purely the inefficiency in the way building components are manufactured. So extrusion is the most obvious one, where you'll take the steel beam of a building component and you'll extrude it uniformly. As you can see in this finite element analysis of a beam under load, you need more material in the center of the beam than you need at the ends. And you need more material where the beam is resting in compression on its support than you do anywhere else. So ideally, those flanges would be changing dimension. The depth of the beam would be changing dimension. The quantity of material would change dimension. And even better than that, the orientation of the materials at a fine grain, even a molecular grain, would be oriented. So we're faced with having to build with components like this, which are very coarsely engineered because of their manufacture. So one of the things that happened in the 80s is digital methods entered into architecture. I mean, frankly, digital methods were mostly invented by architects for visualizing complex coordination of components and systems. And all kinds of things have come up. I'll talk about 5 new developments that have come with the digital, but primarily what's happened is a higher degree of complexity and a greater control of detail and dimensional accuracy is now possible. So for the same price as you would build a conventional building, you can now build a more complex, more dimensionally accurate building with the same schedule and timeline. This is one of the ways you do it. This is what's called a BIM model, a building information model, where not only is it built as a high fidelity 3D file, but also each one of those elements has metadata attached to it. So you'll know its weight, you'll know something about its construction, some of its performance. You can find collisions between elements. You can find the way things interact. It becomes a digital ecology for analyzing complex structures. But as you can see, all the bad habits that preceded it are in these kinds of BIM files. They tend to be highly modularized, highly repetitive, and the majority of architects invest time to develop a model like this to expedite the production of two-dimensional drawings, which is ironic. So for me, I would say that complexity and detail are not really what's interesting. It's what you here with nanoarchitecture is referred to as interactions, but it's the fine-grained connections and interdependencies between things rather than just a high degree of detail. So for me, the high-fidelity 3D model lets every component of a building be different. So this is a building we built in 1999. It opened. Every single piece of steel is a unique length. Every single connection is unique. It was all managed by a high-fidelity 3D file. And at the time, we were pushing the envelope over what you could do in terms of a structure which was not modular, but had a kind of repetition and variation which was integral to the whole design. So that you can see every single element flows sequentially one to the next in a pattern, which was very fluid. To me, I would negatively refer to this as a tectonic structure, which means built out of layers of components. Shortly after that, in the late 90s and early 2000s, I started to work with machine code and connect these 3D files directly to the machines that were manufacturing components. And this idea of going direct to manufacture by speaking a machine language rather than going through a conventional design process of producing drawings and defining dimension and shape was very important. You may wonder, why are we doing this to this poor duck? It's probably the closest to the kind of questions of accuracy and tolerance that you're talking about at designing things at an atomic scale. What we did is we did a high fidelity laser scan, grabbed the digital file, arrayed it into a complex array. This is around 300 components, and then custom cut each one of those components and welded and nested them all together, as you can see with these structures. So we started to rethink masonry. Instead of modular uniform bricks that would stack, these were these hollow plastic bricks which could get arrayed and intersected in a complex way. And we never did a drawing of this. We always went straight from the 3D. We then developed an interior wall system with a company called Panelite, and these are around at hotel lobbies and interiors and things, where we could make our own bricks and cut all of those things custom, and we've done them at all kinds of different scales. But it's an approach to construction which is very non-modular and bypasses entirely this need to think in drawings. Procedural design is something which is revolutionizing our industry, and this is getting right to the point of not designing something, but designing a process. And that process needs a little bit of perspicacity, or knowing what you want in advance. But once you do that, you can start to write scripts and design with scripts and algorithms rather than making shapes. This is a recladding of a facade of a building from the 1970s in the Netherlands, where we were building a structure to support stairs and a few escalators on the facade. What we did is defined a construction system of components which involved steel trusses, cladding, and supports for the stairs and escalators. And we then described those in a series of dependencies and relationships in, at that point we were using a MEL script. We then could locate where the points of support needed to be, and all of the components surrounding those points of support would then modify. So as you can see, kind of step by step, we would locate a point in space which corresponded to the existing building, floor by floor. we would locate a fixed angle of one of the components of this vertical truss that would get arrayed. We would array those at each floor elevation of the existing building. Then based on what they needed to carry in terms of the weight of the escalator, we would locate points that would change their dimension. And you can see how those arrays would begin to work. Each one of the components, every steel detail, every piece of information you needed to manufacture was built into that simple code. And then you could procedurally run through endless design solutions in this kind of algorithmic procedural space. So, and that's how we came up with the design over the length of this nearly kilometer-long building. More recently, I've gotten very interested and involved in bringing composites into architecture, meaning structures built out of textiles, where you can begin to define structural performance based on the orientation of fibers. So instead of looking at sections of steel, we're now looking at sections of fiber. And we're getting towards a much finer grain design system. So here you're looking at shells primarily, non-isotropic shells mostly, and you're strengthening and stiffening them by locating fiber. The first use of this kind of technology for me in a building was this luminous ceiling at a house in Southern California, where we built it actually with a boat builder. And through that relationship, I started to learn more about how they were locating fiber using robotics, so that instead of buying cloth with say a 0-90 or a ±45 orientation, you could actually come up with a bespoke kit of cloth with the fibers oriented in the load paths of your surface. So here is a beam. Here's a beam. If we support the beam at its center and one end, it deflects less than 1 centimeter under 13 tons of load. At the center of the beam, there are roughly 120 layers of carbon. At the ends of the beam, there are about 6 layers of carbon. So, and this entire element, 2 of us could carry around, weighs about 150 kilos. So this is an example where by orienting the fiber, this comes in at a fraction the weight of its equivalent steel. But what's most important is you put the material only where it's needed and only in the alignment that you need to put it in. The way the material gets placed is very similar to this. This is a video from North Sales in Minden, Nevada, who we work with a lot. They'll build a lot of our fiber composite layup. So this is an example of a robot laying down about 7 strands of carbon tow in a bespoke orientation on a deformable mold. So they can jack this mold up into shape in less than a minute and then lay that fiber down. They even vacuum bag and consolidate it with a heater on a gantry as well. So and the reason that I'm interested in them is they are working at a scale of a building, so they can build large components. This is an even finer grain material. It's a carbon tape that's 0.08 mil thick. And they're laying those tapes down with these gantry heads in whatever bespoke orientation you would like. And the bed size there is about 25 meters. And they can even do a little bit larger. But so you'll see that head, how it's laying down the tapes at whatever orientation your forces are located in. This is a sample of the material. It literally falls apart in your hands. We've used that to make, I think it's the lightest chair anybody could make. What's nice about it is this material has a property where under no load, it takes a compression shell shape. So it's in the shape that it was molded on, and it's molded for a person to sit in it. But the minute you sit in it, it turns into a soft fabric and a textile structure. So the engineers we worked with on this classify it as a compression structure under no load that then converts to a tension structure under load, all in one system of plies. We took that same material, and we've been working with Nike for the last year and a half. We're about to roll out a series of these chairs for the NBA for 3 teams this next season. And we've input data and information now into that carbon composite layer. So we worked with Nike and some of their athletes. That's Alessandro Gentile. There he is in the chair. These athletes have a problem that the coaches and trainers want to know their state while they're playing the game, but they come off the court for such a short time. If you want to change their state, you only have a little bit of time to do it, and you want to pull the information off of them so you know how long they can keep playing and how hard they can play. So we took an actual NBA player, molded digitally this surface on that player. We combined 2 types of resin, so the chair is rigid around its perimeter, and it's flexible and soft in the interior. And we embedded in that Peltier chips and temperature sensors and weight tension wires so that we could pull data off the athlete to know if they've lost weight, which means they're depleted of water. We can take their temperature all over their body, and we can also change the temperature of the athlete selectively. You can see we put heat sinks on the back of it to take away some of that heat. This is a thermal imaging camera of the chair, and you can see that as we change the charge in the Peltier chips, we not only change it locally, but change the whole surface of the carbon because it's so thermally conductive. And what you want to do with these athletes, you want to, when they come off, you want to heat them up, which is very counterintuitive to an athlete. They don't want to get in a chair that's going to heat them up. But you need to heat them so they don't cramp. But then you want to make them feel cooler. So we cool their spine and blow air on their face while we heat their legs and heat their shoulders and arms. This is the first prototype of the chair with a thermal camera on it. And you can see we visualized it with the camera, but we're pulling data off of that. But so this idea of a fine grain, highly engineered, lightweight structure, which is filled with data collecting and also is a kind of a microclimate that changes the state of the people within it. For me, this is where architecture is going, and this is the kind of performance that we're expecting from materials. A company like Nike has not only the financial resources to develop this, but they actually have the physiologists and athletes, which it makes a lot of sense to develop this with. But I really think that this will be the normal that we'll be thinking about in the built environment in probably less than a decade. I mean, the interest of automobile company and furniture companies in this kind of a material is very important. I would say it's still very coarse in the sense of the systems, and in the next round, we're hoping to integrate more of the mechanics and electronics into the actual materials. The other thing that's really changed the fineness of design is that architects, and this is an important thing, and their teams tend to work in a static model. Like, we always want to eliminate forces into discrete problems and solve those things with no reference to wind, gravity, etc. We like to attack each one of those problems independently, not as a composite. And for the last 15 or 20 years, we've been able to use computational fluid dynamics, which lets us think of space not as an inert static space of geometric points, but actually is something which has temperature, which has air movement, which has gravity, which has all of these forces in it. So when I design, I'll tend to design in a space which has some simulated physics in it. And the ability to design in a space with simulated physics is very different than in designing a space of three-axis coordinates. So the most extreme example of that is a boat. I designed a boat for myself along with a naval architect, but it was using all these tools we've been using as well as some of the materials. I believe it's the first boat to couple aerodynamics and hydrodynamics. We did this with a 7-variable FEA. 3 of those variables were in the water, 4 of them were in the air. So we could literally design a form, drop it into this environment, and it just takes off. So it never takes off well because nobody's driving it. But we learned a lot from this process of exploring coupled hydrodynamics and aerodynamics. All of the surfaces were modeled and run sequentially through FEA so that the shapes are hydrodynamically and aerodynamically refined. It was all built without any drawings. So this is a giant CNC mill that cut out this 13-meter long form. There are about 8 of these pieces of formwork. And then as you can see, here's the best example I have of how this bespoke placement works. This strap is a very important moment in the boat. You can see these taper lines where you're going from layers of carbon to layers of carbon. So instead of having one extruded plate of material, here you're starting to step this plate back with maybe 20 different steps of just conventional carbon material. Same wherever there's a hole, the hole's getting reinforced with progressively step back plates. That's all cut with a robot controlled knife. So the builder gets all those components pre-kitted. That's the final shape. What's great about it for me is, this is a thing that goes about 55 kilometers an hour just with wind power. And all of the verification of what we were studying in the computational finite element analysis is actually what you see when you go out sailing with the boat. Exactly the buoyancy and foiling that we were simulating, we were seeing. So it's incredibly reliable. Reliable enough. I take my teenage kids out at 50 kilometers an hour with no adults. So it's a mature space that buildings are just starting to use for design, where you can simulate physics now and start to get down to very fine-grained structural decisions using physics. So finally, the last thing I thought I'd bring, and this is probably the furthest from nanotechnology, but you may see something there. I'm interested if you do. I co-founded a company in Boston a year ago to look at transportation in North American cities. And I did it along with Jeffrey Schnapp and the Piaggio group, who were the inventors of the Vespa scooter. And they wanted to get into autonomy and start thinking about self-driving and wanted to know what the right scale to think about that was and what the markets were. So in the process of working with Piaggio over the last year, we've come up with this term we use all the time called granular mobility. And I think it might have something to do with what you're talking about with nanoarchitectonics. And it's really about reducing the scale of the way we think about things moving in the cities and going to a denser and finer and more intelligent system of transportation. So I show my team all the time videos like this. This is in Hanoi. If you put every one of those people in a car, you can imagine what kind of a traffic jam you have at that intersection. So for us, we say San Francisco, Boston, New York is going to look more like Hanoi, and cars are not going to be the answer. That we want to think of an alternative to a self-driving car, something finer grain, and where you don't have this segregation of vehicular space with bike lanes with pedestrians, but it's all one space. To do that, we've thought about these lightweight vehicles. We really think we want to have the right size vehicle for the right mobility problem. And very early on, we started with this diagram where we said, let's be in the space of a scooter, which is smaller than a self-driving car, but bigger than an aerial drone, but has the intelligence that those two autonomous vehicles have, but just at a much smaller scale. Because if you want to deliver groceries or a pizza or a typical package, it's ridiculous to do it out of the trunk of a car. It's too big a vehicle for that problem. So here you can see the first vehicle we've done. It's called Jita, next to a scooter, so it's even smaller than a scooter. In terms of how we're building these, we have a microfactory in Boston. We're trying to approach manufacturing with as many on-demand parts as possible. So we have an array of carbon 3D printers. It's engineered by motorcycle race engineers. So it brakes and accelerates in corners like a vehicle, not like a robot. It's 100% carbon fiber. This is one of those carbon fiber printers. Each one has 78 components, which we can print with our array in less than a day. And the thing that's unique about them is they're navigating with a person all the time. It's a vision-based navigation system. So you can see here what we're pulling off one of those robots. It's got 18 cameras on it. And as it moves through space, it builds a three-dimensional map of the world and takes a path through that world by following a person who has the same camera arrays on their belt. So it's leveraging people while using autonomous robotic technology for navigation. So it has the fine-grained movements of a person. It turns in zero radius like a person. It goes 22 miles an hour, which is how fast Usain Bolt goes. It can also crawl really slowly. So everything it does matches a person. Here you'll see 3 of them following 3 of our staff. But for me, this smaller and smaller approach to the problem, I think you see it everywhere. I think so for us, for cities, we're really thinking, how do we not solve every problem with a car? How do we go to something which is smaller and intelligent and is both getting information from the person it's following, and also they have vehicle-to-vehicle communication, so they get information from each other. And you can see they're self-balancing and they're hollow. The whole inside is all for carrying stuff. So to kind of explain to our customers what this would do for a city and how this would be of value to them, we did this short little movie, which is really about a finer urban infrastructure. And I would say, if there was a word that I'd like to come away from this few days with, it's of a nano-urbanism, that thinking about a transportation which is finer grain and non-automotive, but more about passengers, or more about riders than passengers. That's what we tried to show with this short little film. I think if you applied that Feynman quote to cities, you would have to admit things are getting denser and denser and smaller, and that we have to start to have solutions which are looking at more and more numbers of littler and littler things. In this case, it's going to things with 2 wheels or 3 wheels rather than 4, going to things that are the size of a person rather than the size of a garage, and trying to think more and more about everything from urban infrastructure down to the materials we build with, with a finer grain attitude and more efficiency and intelligence, I would say, in all those vehicles. Okay, that's my bell. Thank you.